Hey guys, it's Monday morning, and we're analyzing neural nets that compute low-dimensional binary functions because there's no reason to do this. So anyway, this is the current function that we're computing, and yeah. So basically, what we're saying is like we're trying to understand what each layer is doing, and we're also kind of trying to predict like what the weight arrays will actually look like. And we're having some success, I have to say. Like my previous stream was pretty good. That one I had already figured out mostly the neural net. This one I have not figured it out. So it'll have more drama. You know, because it's like, can a human figure out a 37 parameter neural net or not? You know, and at the end of the day, it'll probably be a mixed bag. But so anyway, this is the function that we're computing, right? This is a randomly selected function, and yeah, it's it doesn't really. It possibly has a semantic interpretation. And anyway, this is the visualization. This is the neural net. So it's like at each layer, we sort the rows, the inputs, according to clustering, like the outputs. So like these are the outputs of this layer. These are the inputs. So like these inputs are the raw inputs from the previous layer. And then like these outputs become the inputs to the next layer, right? It makes sense. And then this is the target function. So it's a little hairy if you haven't seen it before, but so anyway, yeah, we're gonna work backwards on this guy. And so like one immediate, right, so like this is the last layer, and this is the output, and this is the target function. So we can see that it is correctly implementing the target function. Another broad observation is that the inputs here, for the blue rows, we have two different points, right? We have like blue, 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 red, and blue, red, blue, red. We're we're ignoring some magnitude fluctuations. And for the red rows, we have 3 active points, for a total of 5 points. So that's one thing the previous layers have done, is they've mapped 16 points to 5 points. And the whole time we're in 4-dimensional space, because like we have 4 units per layer, except for the final output. And but it's a general principle, and probably in some way that you could like quantify that, like if you're trying to fit a hyperplane between like binary labeled points in really any dimensional space, like it's always easier to do that the smaller number of points that you have. Okay, so yeah, those are broad observations. We will now, actually I already, we will now attempt to understand the actual weight vectors for this layer, for layer 4. So like the actual, like you can interpret it geometrically as a hyperplane, or you can interpret it more like computationally, just in terms of like the actual dot product computations. So I already know what the weight vector is because I already looked at it. And it turns out to be, or also we're just going by the sign patterns. So, yeah, so anyway, the weight vector here is like red, blue, red, blue. And, right, so like kind of the interpretation, I mean, it's kind of like, it's not clear this is useful interpretation anyway, but I mean, you can see how red, blue is working, right? Because, like, red, blue on the first two columns is going to cancel, and then you're going to pick up, like, a negative value and a negative value. Like, blue is -1. So, like, if you multiply a negative and a positive, you get a negative, and so forth. Yeah, so, like, these points are going to be negative because of the red, blue. These points literally are red, blue, the negation of red, blue. So they're going to be very negative. And then, like, this point is like an odd man out, because red, blue is going to cancel on the first two columns and then cancel on these two columns. So basically it's like the bias is why this guy is red, because he's getting like, he's getting like a 0 contribution from the dot product with the weight vector. And yeah, and then you just, red, blue, that's a positive, and then a 0. Red, blue, yeah, okay, so that's kind of, right, like, that's kind of mechanistically an interpretation of what the output layer is doing. Yeah, I mean, like, it's not, it's not like a human could look at that and go like, oh yeah, I can now implement my own neural net, but that's fine. So anyway, yeah, let's look at the previous layer. And yeah, I don't know the weights for the previous layer. And yeah. So the inputs for layer 3, there are like 1, 2, 3, 4, 5, 6, 7, like 7 different points. And we, again, like these points and these points are the same points in a different order. So we know that we're going to go from 7 points to 5 points. So there's like 2 points that are going to be mapped to I mean, actually we can already see that in the top rows, like red, blue, blue, red goes away. It maps to this point, and also this point also maps. So I mean, like, these 2 points were distinguishable, and now they're not. But anyway, yeah, like the interpretation, really the only the only interpretation that I can come up with that's actually useful is like the error correction interpretation. So it can kind of make the observation that, like, this last column, if you negate it, which is easy to do with a weight, like you multiply by -1, it's equal to the target function except for 1 row. And yeah, you can do that like for every layer. And I mean, like, you can go back to this layer and be like, okay, which of these columns is most like the target function? That one's a little harder to eyeball. Yeah, but anyway, using that interpretation, we can yeah, I don't know. But anyway, like you can ask, okay, like how are we producing this column from these inputs, right? Because like this is, again, this is almost the target function. So, yeah, how are we producing it from the inputs? I guess that seems like a useful thing to ask. And yeah, like you can immediately make the observation that like this column is it's almost the same as this column, except for these two rows. So it's possible that what this column is doing is like it's putting a large magnitude weight, positive weight, because the signs match. It's putting a large magnitude weight on this column, and then it's making it so that the other three columns are doing like error correction, which means that they will overrule this column only on these two rows. So like it's, so like the single weight vector itself plus all of the previous weight vectors, previous layers, are error correcting this column to produce this column, which is more correct, has like two less errors. So yeah, then it's just kind of like you have to see if you can intuit a weight vector that would do that. I mean, the obvious weight vector would just be like red, red, blue. So like, yeah, so you'd have like red, red, blue, and then red. And right, because you need this to be blue. So like red, red, blue. The problem is that gonna like you don't want it to overrule like on other columns. So like if you do red, 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 blue, that'll still give you a negative. I mean, red, red, blue will give you negative on all of these, which I guess is what you want. So then if you go up here, you get like, yeah, but like it'll also give you red, red, blue. Yeah, I mean, yeah, so it's not easy to see if that's possible, but because yeah, I mean, like it's gonna depend on the magnitudes, not just the sign patterns. But anyway, okay, so we'll just look at those weights. So hopefully it's like red, red, blue. Yeah, okay, so these are layer 3 weights. This is the last column. So we get red, red, blue, red. But yeah, like it is depending heavily on the, because like this is a huge magnitude. I mean, yeah, like you could try to, I mean, yeah, like, if you go by like the largest magnitude weight, like we're picking this guy, so we're saying like this last column output is equal to this guy Um, which is true up except for this group of points. And then the other weights are red, blue, red, 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 blue, red, which is matching that pattern. Red, blue, red. Yeah, I guess that makes sense. Yeah, I'm not sure this is useful to fucking do. Or, I mean, like, either interpretation is good. But yeah, let's just run with the largest magnitude weight. I don't know. I mean, there's two things. There's like the largest magnitude weight, and but then there's also the column that most closely matches. Yeah. So. Right. Yeah, but then, okay, so then it's like, what do the other columns do? I mean, because they're, I mean, yeah, I mean, if you look at the last column from like an error correction perspective, it's like, you know, like this column is correct on everything except for this one guy, this one row. This column is also correct on everything except for this one row. And the error correction that the last layer is employing is that, you know, it's doing the weight vectors are like red, blue, so they cancel. So what it's saying is that, like, the requirements for these columns are that, yeah, like, you I mean, it's kind of like what it's doing is it's doing like I mean, if you take the closest column perspective, what this column is doing is it's doing error correction on these two rows. But then it's like maintaining kind of like a tag on this, on the one remaining row. which I guess you could interpret as like on these three columns on like this three-dimensional thingy. It's you just have to separate like blue, blue, red. Like whenever you have blue, blue, red, you have to make it positive because like it wants because like the negation of this column is closest, so yeah, like you have to like make it but the point is that you can always separate like a single point from all of the other points. Blue, blue, red, although that is not actually what that layer is doing. Well, yeah, no, it's not. Red. Yeah. Um, yeah, well, okay, let's just try to interpret the weight vectors. Maybe that'll make more sense. Okay, so we saw that this column, if you go by the largest magnitude in the weight vector, you know, it's saying that this last column is the second column, and with error correction on these rows, yeah, so like the sign patterns is, yeah, you want it to be like if it's red, blue, red, you want it to be positive, like you want it to overrule this, because otherwise this is a large positive weight. So you need blue, red, blue to override, and you also need red, red, red to override. Yeah. I mean, it's kind of close even, because if you're just looking at red, 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 you need it to override, but then yeah, like you need it to not override down here. Okay, so yeah, it's like, alright, it's this column with various overrides. Okay, so let's just go to the first column. Yeah, the first column could be any number of, let's just look at what it is. So we're on the first column, so now we're looking at the first row. First row, and again, like the largest magnitude. So this is almost the negation. Like in sign pattern, it is the negation of this row. Right. Okay, so yeah, like these two columns are actually negations of each other. Who knew? Okay, so those are negations of each other. Great. We'll look at this column. What's happening with this column? Yeah, another thing to note is like this column is only accepting 2 points. So it's accepting all reds and red, blue, red, blue. Which is not entirely clear that that's linearly separable. But we don't have all of the points, so maybe it is. Okay, but yeah, alright, let's look at the second column. So, yeah, the largest magnitude on the second column is on the first column. Yeah, so I mean, you have like the weird thing where the outer columns are paying most attention to the second input column, whereas the inner two columns are paying most attention to the first input column. So in particular, yeah, actually, I mean, yeah, I didn't really notice that, but yeah, if you look at the second column, it's identical to the first column except for this one input. So it's, right, so like all the other points are blue. So they're saying like the second column is this input column. But if all of the other points are red, we want you to be a blue. So like, yeah, it's being overridden, yeah, on this one row. That is in fact the error row. So you could kind of interpret that as having to do with tagging, like error tagging. The third output column here is like also this one. Except it gets rid of these and pushes that to red. And actually, right. Okay, so like if we're looking at the weight thing, yeah, it's saying like all of these outputs care a lot about the first and second columns of the inputs. And I guess if you compare, yeah, the first and second, um, I guess, I mean, it's like, like for these red rows, yeah, it's like when they agree, when they're both blue, then you get a red. Actually, yeah, I mean, they are following the general pattern. Actually, yeah, they're perfectly following the pattern of, right, with one exception of if they're not equal, then it's a blue row. Yeah, if they're not equal, it's a blue row. If they are equal, it's a red row, with one exception. So yeah, look, I'm gonna take a break. This was a failure.